All right. Thank you, everybody, for again for joining us this afternoon in the latest of our ongoing series of Safety National UTC webinar series. Today, we're going to be hearing from two speakers regarding work that was conducted on a safety project entitled "The Big Data Methods for Simplifying Traffic Safety Analysis." Our first speaker will be Ali Shirazi from now from the University of Maine, was at Texas A&M earlier while the work was being conducted. But first, a couple of, I guess, kind of housekeeping items. If you have questions that you would like to have answered, we will be answering those at the end of both presentations. Each presenter will take about 20 minutes to present their work, and then at the end, we'll have question and answer. If you want to ask questions, please type them into the chat window, and that's addressed to everyone. And we'll do our best to run through them in sequence once the speakers are completed. So again, our first speaker is Ali Shirazi from was Texas A&M, now University of Maine. And the title of his presentation is Model Selection Heuristics Based on Characteristics of the Data. Go ahead, Ali.
Sure. During the first part of the presentation, we are going to talk about the model selection methodology we designed during the project. The idea behind this strategy is that we have a lot of models and distributions, and using post-modeling methods to select a model between all these distributions that are used for crash data analysis is a tedious task. And so sometimes we face some theoretical issues, numerical issues, issues related to complexities, big data, and data with many zero observation. So technically, we have a lot of distributions. We have a lot of models. If we want to compare them, we need a model selection methodology that is easier than just post-modeling methods, like fitting the distributions and then select a model based on fit. And the other reason is that classical methods based on fit, they don't give us any intuitions about the logic behind the model selection. So they don't address the characteristics of data. They just give us the model that fits the data better. But we don't know what's the reason behind that. Is that because the data is skewed? Is that because we have a lot of zeros? Is that because cortices is high? We don't know the reason behind that. So the motivation behind this model selection strategy is to propose a method that is fast, is easier to use, it's easy to use or simple to use, and at the same time addresses the characteristics of data. So we are looking for a methodology that can be used before fitting the distributions and can be used to select a model or a distribution based on characteristics of data. If I want to give you an example, the simplest example is Poisson distribution versus negative binomial distribution. So when we compare Poisson and negative binomial, we don't need to go and use post-modeling methods to compare these two distributions or select a distribution between these two. All we need to know is the variance of data and the mean of the data. If the ratio between variance to the mean is greater than 1, we go with the negative binomial distribution. If it is not greater than 1, Poisson distribution is preferred. So if you look at this graph here, you can see that negative binomial distribution is used for the situations that variance to mean ratio is greater than 1 and Poisson distribution otherwise. Again, we don't need any post-modeling methods to conclude between these two distributions. We know that based on two characteristics of data, just variance and the mean of the data. So technically, variance to mean ratio or VMR is used as a switching point between these two distributions. Again, no need for post-modeling approaches. We can just select a model between Poisson and negative binomial just based on two characteristics, variance and mean. The other example is negative binomial distribution and negative binomial Linley distribution. We know from several papers that were published over the last few years that negative binomial linearly distribution is preferred when data is skewed or have a lot of zeros. But we don't know when we need to switch from negative binomial to negative binomial linearly. So the idea is that, can we design a rule of thumb, something easy, easier model selection strategy that we call it heuristics, to select a distribution between negative binomial and negative binomial linearly without any post-modeling efforts. So again, the idea is that we want to design rule of thumbs. It may not be completely accurate to find the best solution, the best model, but it will guide us to a likely true model. So if you look at this graph, you can go and do a lot of post-modeling analysis between several distributions to find a true model. Or you can use a rule of thumbs that we developed a strategy or methodology during this project to design simple heuristics just based on characteristics of data to find a likely true or most likely true distribution. And again, the advantage of this model selection strategy is that we look at the characteristics of data. Even if you go with most complex post-modeling methods to select the best model for your analysis, you don't know why one model was preferred to the other one. You know that the fit is better, but you don't know why. Is that because the data was skewed? Is that because the data had a lot of zeros? Was that because the variance was high, mean was low? You don't know about the reason behind that. So I'm going to talk about the methodology we developed during this project briefly. So theoretically, sometimes we can show the relationship between two distributions. Like, as example that is very popular in crash data modeling, we know negative binomial distribution theoretically is used when ratio of variance to the mean is greater than 1. But we don't know this for other distributions, right? So we don't know theoretically why, for example, negative binomial linearly is preferred to negative binomial. Whenever we don't have that availability of theoretical approaches, we resort to computational approach. So the methodology we developed during this project involved 2 steps. The first step is to simulate a lot of data sets from both distributions, several distributions we are trying to compare. We develop, we try to simulate a lot of data sets. For each data set, we record M summary statistics, and then try to run a classifier in step 2 to running a classifier over summary statistics to learn the pattern in data to discriminate one distribution from another. So if I want to explain that more clearly, assume that A1 is one of my distributions, like negative binomial, A2 is the other one, like negative binomial linearly, and AR or several other distributions are other distributions, like negative binomial generalized exponential or negative binomial Dirichlet process. So several distributions. For each distribution, I try to simulate millions of data sets. So N here can be like 1 million, it can be 10 million data sets. And for each data set, I record M summary statistics, like mean, variance, the ratio of variance to the mean, standard deviation, cortices, skewness, number of zeros. So these are all the summary statistics that I can collect and record. For each data set, I simulate from each distribution. So I do that for the second distribution. In this case, let's say that it's negative binomial linearly. Again, I simulate N data sets. N can be just 1 million data sets. And for each data set, I record M summary statistics. Again, it can be mean, variance, variance to mean ratio, range, quantiles, interquantiles, all these summary statistics. And in step 2, I run a classifier over the big data I generated over these summary statistics. So technically, the matrix X is the summary statistics that are correct, that are recorded. The vector Y is the label of the distribution. I run the classifier over summary statistics for matrix X to classify the outcome. And the outcome is the distribution label. Like, for example, the label can be negative binomial. It can be Poisson. It can be negative binomial Lindy. So again, the method, the idea behind the method is to simulate a lot of data and then run a classifier over these data sets that they're generated and summary statistics that were recorded to distinguish one distribution from the other distribution. Or in other words, we are trying to have a new look at model selection. We look at model selection as a classification problem. So let's look at this example. For example, we simulated data sets from Poisson distribution and also from negative binomial distribution. And then we recorded summary statistics. We simulated millions of data sets from Poisson, millions of data sets from negative binomial. We recorded summary statistics, like M summary statistics for each data set that are generated from Poisson, each data set that are generated from negative binomial, and we run a classifier. In this case, a simple decision tree classifier. And if you look at the results, it's very similar to the theoretical results. Theoretically, we know that if the variance to mean ratio is greater than 1, we need to go and use negative binomial distribution. In this case, it's very close. It's 1.06. And also, if we tried, so LRT or likelihood ratio test is one of the most powerful tests in statistics under certain circumstances, under certain conditions. If we try to draw a graph of the relationship between VMR or variance to the mean ratio and the likelihood ratio test or likelihood ratio statistics, we will see a strong correlation between these heuristics and the most powerful tests in statistics. So what I'm trying to say is that to go and use likelihood ratio test, it's a tedious task. We need to do post-modeling to come up with the best model. But looking at just the ratio of variance to the mean is not difficult. It's a simple approach. But we have a strong correlation between these two approaches. In other words, the heuristics we are developing here, they are valid, valid points, valid, they have values. So let's look at another example. I tried to compare Poisson gamma or negative binomial distribution with Poisson log normal distribution. And this is the decision tree outcome. So we realized that the number of zeros and the cortices of the data sets are the most important characteristics that we need to look at to distinguish between Poisson gamma and Poisson log normal. So during the previous literature, several literatures show that when the number of zeros are higher, PG or negative binomial distribution is preferred over Poisson log normal in the past. But they didn't know when we need to switch between these two distributions. Using this approach, the new approach that we developed here, and looking at this decision tree classifier, we know that, for example, if cortices is greater than 18.5, we need to go in this branch of tree and then follow up until we know what distribution we need to use. Again, it's very simple to use this decision tree or heuristics. We don't need any post-modeling approach to come up with the best model. Anybody can just find simple characteristics like variance, mean, coefficients, zeros, number of zeros in the data set, and use this decision tree, simple decision tree, to come up with a model to analyze his or her data. So this is the general outcome of this decision tree. When number of zeros goes up, negative binomial distribution is preferred to Poisson log normal. When coefficients goes up, Poisson log normal is preferred to negative binomial. Again, previous literature showed this outcome, several research studies, but they didn't know what's the switching point. So if we use decision tree classifier, which is not an accurate classifier, we see about 10% error in our classification. For 90% of situations, the classifier works well. For around 10%, we have some errors. We can use a better classifier, like random forest classifier, to distinguish between these two distributions. And if you look at the results, the error here is less than 2%. So sometimes it's better to use a better classifier like random forest. Although, like, you know, for decision tree, you can see the results in a graph, which is very easy to understand. But for random forest, unfortunately, you cannot show the results graphically. It's a black box technique for classification. But one of the byproduct of the random forest classifier is to prioritize important variables. Here our variables are summary statistics. You can see that percentage of zeros, skewness, and coefficients are the most important summary statistics to distinguish between Poisson gamma or negative binomial and Poisson log normal distributions. So again, with previous model selection strategies, we didn't know why one model was preferred to the other one. Now we know that it's because of percentage of zeros, skewness, or coefficients. Another example, negative binomial and negative binomial linearly. We knew that negative binomial linearly was preferred when skewness was high, but we didn't know when we need to switch from negative binomial to negative binomial linearly. Now with this approach, we know that. If the skewness is greater than 1.92, we need to shift from negative binomial to negative binomial linearly. And again, we can use a random forest classifier and know that skewness, coefficients, and number of zeros are the most important characteristics to distinguish between these two distributions. So look at some results here. So I just show you the results, the model selection results for Texas rural two-lane horizontal curves using classical tests like chi-square and log likelihood ratio tests and the heuristics. For classical tests, we need to do some analysis. We need to fit the models and then find the log likelihood ratio or log likelihood test and chi-square to select the model. Here with the heuristics, we just need to look at the characteristics, but the result is the same here. This is another example for Toronto data, signals intersections in Toronto. And again, we compared classical tests versus heuristics. For classical tests, we need to do post-modeling and find the best fit. For heuristics, we don't need any post-modeling. We just look at the characteristics of data to come up with the best model. But the results, we realize that are the same. So either if you go with the post-modeling method or our heuristic, you will come up with negative binomial distribution as a favorite distribution to model Toronto four-leg signal intersections. So if I want to compare the heuristics method with the classical one, I'm saying that we try to switch two things between them. So for the classical test, we have complex test statistics, but simple decision criteria. So to develop test statistics, we need to fit the models, right? We need to do post-modeling approaches. But the decision is very simple. Usually you know the distribution of the test statistics and you can select the best model. For the heuristics, the test statistics is very simple. We just need to know the characteristics like variance, mean, skewness, kurtosis, number of zeros. These kind of simple test statistics. But the decision criteria can be very complex. So like, for example, if we use some advanced classifications, it's a very complex classification to come up with the best, to distinguish one distribution from the other one. So technically, we are trying to switch between these two tasks, between test statistics and decision criteria. But why this method? I just want to conclude my presentation. So there are several advantages to use the heuristic method instead of post-modeling approaches. First of all, we examine the characteristics of data. Majority of previous statistics methods, they just look at the fit. They didn't give us any intuitions why one model or distribution is preferred to the other one based on the characteristics. We can use these heuristics before fitting the distributions. So we don't need to face some numerical issues we may have with distinguishing one distribution with the other. It's simple to be used. It's quick guidelines. Like, if you are doing something practical and you don't want to find the exact model, it's a quick guidelines to find the distribution that you need to fit your data. No issue with complexity. So different distributions or models, they have different complexities. And you need to consider complexities when you do model selection. But in our approach, we integrated out the complexity. We just look at the characteristics when we come up with the distribution. And the last one is about big data. So in the future, we have, or even right now, we have big data coming to the system. And we want to have a quick selection of the model. We want to select one model immediately and just fit the data based on that. So this approach is good because you don't need to fit your model based on that big data you have to come up with a model. We can just use simple heuristics or simple selections to select the best model. But of course, the major limitation of this approach is that it's a rule of thumb or it's a heuristics. So most likely you will come up with the best distribution to be used. Not best, I mean like, the good model to be used, but it's not, but it may have some errors. If you use better classifications, then the error is less than the simple classification methods like decision tree. Thank you very much.
All right, thank you very much, Ali. Appreciate that. As I mentioned before, I think we're going to reserve questions for the individual presenters until the end of the whole session. If you have any questions that you want to pose now so that you don't lose track of them, feel free to open the chat window, and you can find that at the bottom of your presentation screen from the Zoom window, and then type in your question and we'll get to them one by one at the end of the presentation. So our next speaker is Fang Guo from the Virginia Tech Transportation Institute, and his presentation is Rare Events Modeling. Fang, go ahead.
All right, great. This is a work with our research team, me, Professor Xinwei, and Maggie. So one of the issues in traffic safety modeling is crash or rare event, which means total number of crash are typically very limited. And especially when you look at those recently emerging new type of crash data, like SHRP2 NDS with a study that size, by the end of the day, we only have less than 2,000 crashes. And some of the typical high severity crashes, level 1, level 2, we have only less than 300 of those. So the rarity of the crash pose a lot of issues in prediction and estimating the effect of certain risk factors. So this project has two focus areas. One is predict individual driver risk based on telematics driving data. So we develop a decision-adjusted optimal prediction models to predict a small percentage of really high-risk drivers. Most of my talk will focus on this area. The second focus area is a finite sample bias. I will talk about Poisson negative binomial or the dominant models in safety modeling. But what we have shown is when the number of crashes are small, the parameters are biased, which will lead to inaccurate estimation of safety countermeasures, things like that. So predicting risky drivers. So if you look at the individual crash risk at the individual driver level, a common known fact is what they call the good driver, bad driver behavior. So essentially, most of the driver, majority of the driver, more than 80, even 90% of the driver, their risk is actually fairly low. And this is some actual data. But if you look at a very small percentage of risk drivers, 5, 10%, even 1%, their crash just skyrocketing. So if we can successfully predict which driver is at high risk, it will give us a lot of information to support driver education, fleet safety management, team driver coaching program, and insurance pricing. So traditionally, how the driver crash risk was done is based on demographic information. So those are the variables collected through SHRP2. This is probably the most comprehensive traditional predictors you can get. We got very detailed demographic information. We have their driving history, number of crashes, number of violations, and we have surveyed their personality and the sensation-seeking scale. So the traditional individual crash risk model are typically based on this, but there are issues with each one of them. For example, demographic information, they typically give very large group. For example, age and gender group, those two are, you could have large amount of drivers that share similar characteristics. And the number of crashes, traditional crash history suffers from regression to the mean fact. Number of violations are very sparse. The survey results are typically not available. In this project, we're trying to use telematic information to as a supplement or complement to the traditional crash predictors and try to build a model to predict driver risk. So the telematics data are become more and more widely available. For example, in SHRP2, we collect speed, acceleration, geolocation, ER rate. Those data are typically very high frequency, 10 Hertz above. So it provides pretty rich information about driving behavior and driving environment. And those type of data are not only from NDS, connected vehicle, GM OnStar, some of the ride-hailing apps, they can all collect this telematic data from a large quantity of drivers, very large driver populations. So one of the most commonly used telematics data are the high G-force event, which here I show is essentially when there is a high acceleration, high deceleration, go beyond a certain threshold. So those could be caused by a lot of factors. For example, late braking, rapid starting, sharp turns, or it could be caused by hazardous driving environment. So those informations can indicate the overall crash risk of a particular driver. But one of the million-dollar questions when using telematics data to predict high-risk driver is how large the threshold should be. So this figure shows the results from the SHRP2 NDS, where we have acceleration, we have deceleration, we have lateral acceleration. So if you set the threshold to say 0.3 G, you could have more than 3 million high G-force deceleration events. But if you increase that to 0.5, it decreased to only 50,000. And if you increase to 0.65 G, it become only 4,000, a little bit over 4,000. So why it matters? Well, if we set the threshold too high, there are too few events left. So we lost the density of the data, which are one of the main advantage or motivations to use telematics data for prediction. But if we set the threshold too low, the results are going to be dominated by normal driving, say regular brake, we can easily reach 0.3 G. So there should be an optimal threshold. And also another aspect of driver risk modeling is it depends on the objective. For example, for a fleet with very limited resources, they can probably provide driver education and safety training for about 1% of the driver. And versus another fleet, they might be able to provide training for 10% of the driver. So the question is if those objectives are different, will the threshold for the high G-force remain the same? So to address that question, we developed a decision-adjusted modeling framework. So here we have the traditional input data, crash output, and the traditional predictors. We have the driver risk models, and one of the parameters we are particularly interested in are the threshold for which we define a high G-force event. And when we input the X, Y's, and this high G-force event, we can get an estimate for the probability of crash or crash rate for an individual driver. So the key question is, what is optimal? Well, if we talk about optimal, we have to also look at another aspect. What is study objective? For example, are you trying to look for 10% of the most high-risk driver or just 1% of high-risk driver? And also, what do you consider this model performance is best? For example, we're trying to maximize the prediction precisions. Well, this entire decision-adjusted framework is essentially by adjust the driver risk models and the parameter we're trying to tune and to optimize the study objective. So our basic model is either a negative binomial or Bernoulli distribution or logistic regression. So you got the driver risk in terms of crash rate or crash probability. So to demonstrate this, we use the SHRP2 NDS. We have about 3,400 drivers, 1 million hours of continuous driving data. So these are the results of the optimal, output model. So on the right side, this is the predictors we used in predicting high-risk drivers. So there's a lot of them. So we use elastic net, basically regularized regression to counter the potential multi-collinearity issues. The predictors including demographic information, the survey results, past crash history. Of course, we also include telematics data. There are 3 models we compared. Model 0, M0, are the traditional models without any optimization. So this is the essentially you build a logistic regression or Poisson regression model. M0 is the results. M1 is a model optimized with respect to traditional global optimization criteria. For example, the area under the curve for the ROC curve. The issue with that is if your purpose is to predict a small percentage of drivers, this AUC, they're gonna optimize with global, with majority, with every single driver. So the top 1% many times gonna be sacrificed because just trying to fit a better model for larger percentage of drivers. Where compared to that, our decision-adjusted model, DAM. So this is with particular objective in mind. So here we can see some of the results. If we like to predict top 1% of the high-risk drivers, model 0, traditional model, give us about 67% of precision, predicted precision. Model 1, 64%. And our decision-adjusted model can give us 85% of prediction precision. All right, so which means if we predict there are 1%, 100 drivers, 85 of them actually going to experience a crash. So, to read this table, essentially, if you look at this percentage, and on the left side, this is our goal to predict top 1%, 2% until 20%, and then you can see the proposed DAM model, decision adjust model, consistently beat the existing models. And here's another way of looking at the problem where the targeted percentage of high-risk drivers on left side is the relative improvement over the existing model. The decision adjust model, especially beneficial when you are targeting a very small percentage of high-risk driver, for example, less than 5%, the relative improvement could be up to 30%. And in most times, it's about 15%. So another issue of modeling this high frequency, high G-force event are that so here we have a plot showing the relationship between distribution of deceleration and the speed. They are apparently not linear. And the deceleration actually depends on the speed. For example, it might be really difficult to get a really high G-force when the speed is high. If you are 70 miles per hour, to pull a 0.5 G acceleration is going to be extremely hard. But when the speed is low, it might be easier. So looks like the threshold should be a function of speed instead of totally independent. But once we factor that in, there's a challenge. Now, if we have different speed bands and we have a lot of, like at least 3 types of acceleration, deceleration, and lateral acceleration, optimize all this simultaneously, computationally, going to be very expensive. So we have this multi-stratum iterative central composition design approach to try to tackle this problem. So the key ideas is we have multi-start scheme. For example, we start with a highly efficient Latin hypercubic sampling design. And after find the initial optimal good candidate point, we do a localized minimum. So, and use another design called central composite design. So this is greatly increased the computational efficiency. And here are some illustration of the procedure. And due to time constraint, I will just quickly fly through this. So initially, we partition the entire space, high dimensional space, into subregions. And within subregion, we pick a data points and find within each region what is the minimum value. And after we got that, we're gonna do a centralized local central composite design within that small region to do a more refined search. And eventually we can find the optimal value, basically stratified by speed. So look at, based on this algorithm, we look at the threshold of deceleration by speed. Clearly you can see it's kind of concave shape. The deceleration, what it defines, if the speed is less than 10 miles per hour, define the threshold at 0.5 G will give us the optimal prediction power. And 20 miles gonna be 0.57, around 40 miles to 60 miles is 0.6 G, but once you go about 60 miles per hour, the threshold actually decreased. So another focus of this project is to adjust finite sample bias. So typically we model the crash use Poisson negative binomial. Those are the standard state of the practice in safety modeling. So the regression coefficient basically tell us for every 1 unit of increase in this covariance, what do we expect the number of crash gonna change. But one issue is when the number of observations are small, what you're gonna have is the parameter estimation is actually biased. And we have this bias correction term to add to that. So the magnitude of bias is associated with number of crashes. It also affected the balance of crash count within each stratum of the categorical variables. For example, if the data is highly unbalanced, you have more observations in one category versus the other, the bias is going to be large. So we have this model basically leads to improved bias as improved estimation of the effect of all the risk factors. Okay, so here's the visualization of the results where if we use simulation studies, so a regular maximum likelihood estimate. This is basically how we get the parameter from a Poisson or negative binomial regression. The proper percentage of bias. So log C0 is basically indicator of the how many crashes we're gonna include in the study. So as you can see, the percentage of bias when the sample size is small could be go up to 100%. So if you say, hey, you know, if I put this runabout or other safety countermeasure in place, then you estimate the benefit associated with that. You could overshoot by 100%. So after bias correction, especially among the small value region, you can see the bias are reduced greatly. So there are still a little bit of boundary issues, which when you hit almost zero observation on that case, there's really not much can be done. But I think really the improvement is about log 5 to this log 20 region. Okay, so in summary, this is, as far as you know, this is the first study to provide an optimal threshold framework to use high G-force telematics data to predict driver risk. We have a decision adjust modeling framework that provide much better prediction power compared to the traditional approach. And we have an effective MICCD algorithm to search the global optimum in the multi-dimensional space. And the last part is focus 2 is the finite sample bias adjustment algorithm provide a better estimation of the effect of all the risk factors. Okay, so that's all my talk. Any questions?
Okay, well, I guess our presenters did an excellent job, given that there are no apparent questions. Thank you both very much for your time, and thank all of the participants for taking the time to go through the content. We appreciate it. And let's see, we have upcoming webinars in the future. I'll just announce those real quick. We have another one with Greg Griffin. That topic area will be street noise relationship to vulnerable road user safety. That's on Wednesday, February 12th at 4 p.m. So again, since there are no additional questions, I see a comment from Dominique Lord. I would like to thank both speakers. I agree. Thanks so much for everybody's time, and we'll be closing the webinar now.